All right, so today we're looking at expectation. All right, what can we expect out of a situation? We're going to start with a very basic version of this and then kind of develop more into what is used in things like game theory, which is a branch of mathematics that's used not just for playing games, but for things like negotiations, like negotiating a contract or a treaty or something like that. They use this idea of expectation to look at the overall outcome of what you're doing. We'll also look at an example where we can use expectation to help us forecast in the future, what results might be in the future. Okay? So here's a case. There's a big explanation here. We're rolling a die 120 times. Okay? How many sixes would you expect to roll out of 120?
1/6.
What?
1/6 times 120.
Yeah, 1/6 times 120, right? You would expect, since there are 6 sides on the die, and each one is equally likely, you'd expect to get 20 of each. All right? That's a basic idea of expectation. In this case, because we have a binomial probability situation, which we're going to look at later, okay, the expectation is simply the number of times the probability. Okay? So we're rolling a die 120 times. The probability of rolling a 6 is 1/6. So 1/6 of 120 is 20. Okay? And I start with this because even without any explanation, it just made sense, right? This element just makes sense. But what I want to build on this to look at is the idea of expected outcome. All right, I'm going to zoom in a little bit here. We have here a formula that's actually on our IB formula booklet, and that is this formula right here. Okay, the other one is just a similar notation, but okay. But what we have, e of x is a function. This is our expectation for the value of our discrete random variable, or our random variable x. Okay? This is also used, we can also use mu for this, because it's the mean outcome. Okay? If we were to roll that die 120 times and count how many 6s we got, and then roll it another 120 times and count how many 6s we got, and then roll it another 120 times and count how many 6s we got, the mean of those, the more and more we did it, would approach that 20 that we expected. Okay? So the mean outcome is our expectation. Okay? Or you'll hear it's called expected value as well. All right? Notice the formula, though. I want to break down this formula and make sure we understand. Okay? This n at the top is the number of trials, or the number of different possible outcomes. Okay? So we looked at the probability distribution from your IP. It had the outcomes 1, 2, and 3. So we have 3 possible outcomes. All right? The various scores that we have are each different values of x. So that's what the x sub I stands for. Okay? And then the p sub I is that score's corresponding probability. Okay?
Wait, sorry, what's x sub I again?
X sub I is the individual score, and p sub I is that score's probability. So we're taking each score and we are multiplying it by its probability.
What do you mean by each score? Like,
each possible outcome. Like the one on the IP had 1, 2, and 3. And then you had the probabilities. You would take 1 times its probability, 2 times its probability, 3 times its probability. And then this sum means we're going to add all of those products together. Okay? Yes?
So, for example, like for the expected outcome of a dot, like a dice, or a die,
Mm-hmm.
it would be like 1, 2, 3, 4, 5, 6.
Exactly. Yeah, because you got to roll 1, 2, 3, 4, 5, or 6.
That would be your n or your x.
That would be your x. It would also be the n because there happen to be 6 of them. Okay?
Okay.
But the 1, the 2, the 3, the 4, the 5, and the 6 are all your x's. And then each of those has a probability of 1/6. Okay?
So when you put this in the calculator, it'd be like 1, 2, 3, and you put that as like this variable, and then you multiply that variable by
its probability.
Okay.
Yeah. Okay. Let's look at an example I think that'll explain. Okay. This is an example of how we could use this concept to predict. Okay. Here we have a dairy farmer. He's estimating that next year the farm's cows will produce about 25,000 gallons of milk. Okay. Now, the price of milk is going to change, or the profit that he's going to make on that milk is going to change, because the price of milk changes, the price of feed changes, the price of gas for his equipment changes. All these different things change, so his profit is not going to be constant for the whole year. Okay? So, because of variation in the market price of milk and the cost of feeding the cows, the profit per gallon may vary with the probabilities given in this table below. Okay? Estimate the profit on the 25,000 gallons. All right? So let's consider this. This is kind of how he would set this up, all right? He's kept good records over the last number of years. Okay? And as a result, he analyzes that data he's collected, and he finds that about 30% of the time, he's making a profit of $1.10 on every gallon of milk he sells. Okay? About 38% of the time, he's only making 90 cents a gallon. 20% of the time, he's making 70 cents per gallon. 6% of the time, he makes 40 cents per gallon. And then you have these down here. 4% of the time, he's just breaking even. Okay? He's not making anything. And in fact, 2% of the time, he's actually losing money. Okay? He's losing 10 cents for every gallon he produces. All right? So, that's the situation.
Where did we get the table from? Like,
That's just given. This is what the farmer, in this case, would have to collect the data, figure out those probabilities, okay, and what the different possibilities were.
so the gain per gallon is xi, right? And the probability is pi.
Very good, yeah. These are our x sub i's, and these are the p sub i's. Okay? So our expectation here, the expected value of x, is we take each of these and multiply them by their probabilities. So we have a $1.10 that we're making 30% of the time. So we're multiplying those together. We're going to add to that our 90 cent profit times the 38% of the time that we're going to make that profit. Okay?
So like the table is always going to be given to us, right? Like we don't have to ourselves calculate the xi or pi.
Well, the x sub i's would be given, or you can infer from the problem. Okay? The probabilities you may have to figure out. Okay? And we'll look at examples like that later too, where you actually, okay, you're given a situation, you do have to figure out what is the probability of that happening. Okay? Alright, so now we go on here. We have 0.4 times 0.06. We have 0 times the 0.04. And we have a minus 10 cents times the 0.02. Okay? So now it's just arithmetic. Okay? We've got 0.33 plus that's going to be 27352 plus 0.14 plus 0.024 plus 0 plus 0.002. Okay? Oh, and that should be minus. Okay? So you add all of those up, And we get 68. Wait, did I multiply that right? 0.9 times 0.38. 27 plus 072 would be 342.
42, yeah.
Oops. There we go. Okay. So we've got 67, 91, 93.4, or 0.934. Okay? So that's great. We got a nice number there. What does that mean?
93.4% of. Never mind.
That's the profit you can expect per gallon.
There we go. Okay. That's our expected profit per gallon. Okay? Our expected profit per gallon. We can expect over the course of a whole year, yeah, sometimes we're going to lose money, sometimes we're going to make a lot, sometimes we're not going to make much, but we can expect an average or a mean of 93.4 cents per gallon profit. Okay? So now this farmer knows that, okay, if I'm going to produce 25,000 gallons, what's his total profit going to be? Come on, you guys have calculators. Wake up.
23,350.
Spoiler alert.
Okay?
Sorry, guys.
Listen, you guys need to be practicing with your graphing calculators too. Even just this arithmetic, you need to get so comfortable with your graphing calculators that you're not even thinking about how to do stuff on it. Okay? Alright, so he can expect to make $23,350 this next year off of his dairy cows. Okay?
That's not a lot of money at all.
No, so
Dairy cow.
Dairy farm.
But yeah, it's like chicken.
maybe he has other stuff.
Do you know his life?
Well, yeah,
Okay.
chicken.
He's a dairy farmer.
Eggs.
Okay.
Eggs are not dairy.
Are they not?
No.
What are they?
Eggs are fetus
Which
chickens.
then what are they? But like
They're like not.
Chicken fetus.
They're just not food.
to figure out what.
I'm pretty-
Eat eggs 'cause they-
I know they're in the dairy section in the grocery store, but
But they aren't.
They're not really though.
oh well.
I'm sorry.
Oh, look at that.
I was here yesterday.
What?
Anyways.
I was here yesterday.
Yeah.
Let's look at how do we apply this? Okay? How do we apply this to game theory? Okay?
Eggs are
Game
not
theory
Eggs are not
can
dairy.
tell us whether or not a situation is fair. Okay? When we have an outcome that will benefit one side and hinder the other side, okay? Or it could cost one person, another person gains in that situation, like a trade agreement between two countries, okay? You want that to be as fair as possible. Okay, so you calculate the benefit to the one country, the benefit to the other country, and I mean, it's mathematically you're treating a benefit to the other country as a negative for you. Okay, not that we don't want to help other people, but that's just mathematically how it would be represented. But in order for that treaty to be fair, it should balance out, right? Your benefits should equal their benefits. So if the pluses to you equal the minuses to you, it should come out to equal
Zero.
0. All right? So the definition of a fair game is when the expectation equals 0. Okay?
Zero expectation.
That's
going up to the carnival guy saying, well, if you look at game theory, this is actually not fair.
well, and you would be right because those guys don't make a living by letting everybody win. Okay?
Look at this graph.
Is zero, right?
It's supposed to be 0.
The expectation should be 0.
You know,
Okay?
fair game.
Here we have this carnival game. All right? We pick a number from 1 to 6 and we roll 3 dice. Okay? And we want to roll the number that we picked. Okay? If your number comes up all 3 times, you win $3. Okay? If your number comes up twice, you win $2. If it comes up once, you win $1. Otherwise, you lose $1. Okay? Evidently, it must cost $1 to play the game or something. Okay? So, we need to figure out, first of all, here's a case where we do need to find the probabilities. All right? I've already kind of done this part because we're going to be looking at binomial probability in a minute. Okay? But we have this idea. The probability that you roll your number is 1 out of 6. Okay? So the probability that all 3 of those are 6s is going to be 1/6 to the 3rd power. Okay? The probability that 2 of them are 6s is going to be 1/6 squared times 5/6 to the 1st. But then you also need a combination. Okay? It's actually going to be a 3 choose 2. If you don't remember this part, that's okay. We're going to look at it again in a little while.
Wait, are we we're gonna have on the test questions with where we have to use the combinations, permutations again?
Sure. Oh yeah. Okay. Then for this one, if we only want 1, okay. By the way, this is what goes up up here. The 0.0694, and this was the 1/6 to the 3rd is 0.0046.
How do you know that?
Well, I figured it out ahead of time. So,
We'll
just for speed. We will go over how to do this, okay? If you forget.
Yes.
All right. So then this third one for 1 time, I want to roll my number 1 time. So the 1/6 is to the 1st. That means I'm not rolling my number twice, and then the combination that go with that is a 3 choose 1. And then finally, if I don't roll my number at all, that's just 5/6 to the 3rd. Okay? That comes out to the 0.5787. The 1 time came out to 0.3472. Okay?
What was the 3rd one? Is it 3 choose 1?
3 choose 1, yes. All right. 3 choose 3 is 1, yes. Yeah, this first term, I mean, technically it's 3 choose 3, and it would be 5/6 to the 0 power. That's why you don't bother writing it. Just like the last term would be a 3 choose 0, which is also 1, and the 1/6 would be to the 0 power. Okay. All right, so now we have our probabilities. We've got our whole table set up, which I would recommend anytime you're dealing with one of these expectation problems, you set up a little table like this. Okay, so the expected outcomes here are $3 times the 0.0046. Okay, so that's going to be 0.0138.
How do you figure that out? Do you multiply it?
You're multiplying $3 by the probability of winning $3. Okay?
So don't we do that? We multiply for all of them and then we add up those numbers.
Yes. Okay? So $2 times the 0.0694 is 1388. 0.1388. The last two are easy because you're multiplying by 1, so it's 0.3472.
And once we add these up, if it doesn't equal 0, then that means it's not fair.
That's correct, okay? So there are the different expectations for each value. We add these together, and what do we end up with?
Negative 0.0789, I think.
Yeah.
That sounds right. Okay. So, is this fair?
No, you have
No.
more chance of losing than winning.
Sounds like
So if it's less than 1, it's not fair.
Well, if it's negative
Right.
or positive.
It would just be better on
If it's not 0, it's not fair. Now, if it's positive, it's not fair, but it's in your favor.
Right.
Okay? If it's negative, it's not fair and it's in their favor.
Wait, if it's not fair, does that mean that, like, does it say that by how much? Is that what the 0.0789 is?
Exactly, it is, okay? What does that negative 0.0789 tell us?
That you have a 0.0789 chance of losing $1.
Isn't that how much money you lose?
No?
Winning.
That's how much you're going to lose every time. So you can expect to lose
Just expect to lose Lexi. Okay. Just expect.
Honestly, I should have those.
0.0789 cents or 7.89 cents every time you play.
Terrible game.
Well, you don't lose
You're
that
robbing
much.
us.
So it's going to cost you about 8 cents almost every time you play.
Wait, why 8?
Expect
Isn't
to
it
lose.
0.078. It's approximately 8 cents.
Wouldn't it technically be expect to lose without the negative 0.0789? Because if you're saying lose negative, then it means
I see we don't.
That's correct.
I'm just not
Okay.
saying. Just wanted to make sure.
She's just being precise. That's okay.
Thank you.
So, yeah, the negative is so it's telling us we're losing. Okay? It's not in our favor.
I predicted it.
Okay?
Those sketchy carnival.
All right, any questions about this?
Nope. Can we do homework together?
Okay? We are going to do one together, okay?
Together.
We're going to skip down to number 8. This is the first one on your required IP. Okay? One thing I will comment on this is that the problem is a tad bit vague as far as what it's asking for. Okay? Here we have this game where it costs you $4 to play. Alright? These winning numbers over here do not take into account the $4. Okay? So you'll note what I have written here. Expected return is just the winnings. Okay? So that you're gonna deal with that for part A and B. Okay? Expected result is what you're talking about on parts C and D. That you do have to take into account the $4 it costs to play. Okay? So at this point, I want you guys to work your way through this and see what you can come up with. Okay? Alright, real quick, let's take a look at A and B, and then I'll leave you some time to do C and D. Alright, hopefully A you got pretty easily. Alright? Your chances of winning $10 is 1 out of 6. And this is where maybe put your probability next to it, 1/6. The probability of winning $4 is 1/3, 2 out of 6, right? And your probability of winning $1 is 3 out of 6, or 1/2, right? Okay? So, what they're telling you here in part B is you've got a 1/6 chance of winning $10. So if we're looking at expectation, 1/6 times 10, that's going to be a 1 2/3 expectation there. Okay? All they're asking you to do on numbers 1 and 2 for part B is do the other two parts of this. So it's 1/3 times, what's the outcome if you roll a 4 or a 5? $4, okay? So this would equal 1 1/3. Okay? What about rolling a 1, 2, or 3? Well, you have a 1 and 2 chance, and what do you get if you roll a 1, 2, or 3? $1, okay? So it's 1/2. So now for part 3, we know these give us a 1/2. We know 4 or 5 gives us 1 1/3. And we know 6 gives us 1 2/3. Okay? And we're going to just add those together to get our total expectation. Okay? So that would be 3.5. $3.5, okay? So you can expect to win $3.5 every time you play. Okay?
Even though the game costs $4.
Well,
So either take
we haven't taken the cost to play into account yet. So now take a look at C and D. The expected result takes into account the $4 that you just had to pay. All right?
Should be negative 3.5.
Okay, good. So part C here, if we're making $3.50 on average, but we have to pay $4 every time we play, you're going to lose 50 cents every time you play on average. Right? Okay. So you're going to lose an average of 50 cents every time you play. So after 100 games, you can expect what?
Lose $50.
To lose $50. Okay?
$50.
So you can expect to lose $50. All right?
I'm scoffing.
That makes sense.
Now, I want to take this problem, I want to do this one because I want to take it a step further here. Okay?
Everyone wins.
Let's say this wasn't a charity. So we want the game to be fair. Okay? How could we make it fair? And by fair, I mean this number here. We want to end up being 0.
You say that the game costs $3.50.
All right, that's the easiest way to make it fair. Only charge people $3.50 to play. Because if it only costs $3.50 to play,
Or like increase what you can win.
okay, yeah, or change the winnings. Okay? And we can actually do this a couple of different ways. Do you guys have any ideas how we could change the winnings to make that go up another 50 cents?
Make the winnings more.
Okay, how much?
50 cents.
All of them? Or just one of them? Or
All of them.
all of them?
Yeah.
Okay. So you're saying let's make it 10.50 and make it 4.50 and make it 1.50. Okay? So that'll be times 1/6 times 1/3 times 1/2. What do you guys think about that strategy?
Should work.
Think it'll work?
Well, you're acting kind of suspicious, so I don't think so.
It's
but-
like the way that you shift like the
doesn't
whole
work.
box plot
Yeah.
thing.
Hang on, do you hear?
I hate Lexi.
Hang on, listen real quick.
It's like the whole concept where you shift all the data, like if we used a box plot over like 50 cents, it's like it moves the mean with it,
That's
so.
exactly what I was thinking.
That's an excellent way of thinking about that, okay? This actually does work, okay?
Then no, that's seriously was. I
Good.
swear.
Hey guys, I came up with that.
No, but that actually is exactly right. You know, if you shift all the data up 50 cents, it's going to increase your mean 50 cents. Okay? So that works. And this actually does end up working. It's I think this comes out to like 175. This comes out to 150, and this is 75 cents. So the total here comes out to $4, which is what it cost you to play the game, therefore it's fair. You can expect to win as much as it costs you every time. Okay? Great.
I believe I knew that.
Great.
She did that.
We could, well, did anyone have a different thought? Something else we could do?
You can change the way it works.
You
So
can knock the
for
chair.
$10 it'd be 5, 6. For $4 it'd be 3, 4, and for $1 it'd be 1, 2.
Okay, yeah, we could change the probabilities. So it's like 1/3, 1/3, and 1/3. Okay? Now, that may or may not end up working out exactly right. Because 1/3 of 1 is 0.33. Well, let's just stick with fractions. So 1/3 of $1. 1/3 of 4 is 1 1/3. And 1/3 of 10 would be 3 1/3. Right? So this is if we made it so that, you know, it was 1 and 2. We could even just put the 3 up here with the 6. If we just had two numbers give you each outcome, okay, that's what we're looking at here. The expectation then ends up being 3, 4, 5. So what's the outcome there?
4.
You make a dollar.
We actually would expect to win $1 every time we play. Okay? Which still isn't fair. It's just, we wouldn't mind playing because it's unfair in our favor. Alright? Okay? So that's a good idea. That's a good idea. Another thing that we could do, though, if we left the probabilities the same, is just pick one of those values to change. Okay? Instead of 1, 4, and 10, what if we changed the middle one? So when I'm calculating my expectation, I've got the 1/6 times 10, so I still have the 1 2/3. 1 2/3. I still have the 1/2 times 1, so I have the 1/2 here. But what if I said, okay, I'm not going to give them $4, I'm going to see what I would have to pay them in order to make it fair. So I'd have 1/3 times X.
50? Wouldn't it be like 50?
I'm not sure. Okay, so you see we're changing the payoff for that rolling a 4 or a 5. Okay, what would we want this to equal though?
4.
4. Okay, we'd want it to equal 4. Okay. So we work this out. We subtract the 1 2/3 and the 1 1/2. So that's going to be, let's see, 4 and 3, that's 7. So that'd be 2 and 3, 2 1/2. No. 1 2/3 plus a half is going to be 3/6 plus 4/6 is 7/6. So it'd be 2 1/6. Okay, so we subtract 2 1/6. So now it's 1 5/6 equals 1/3 x. So now we multiply by 3, and we get x equal to 550. Okay?
Can we do number 11?
We're not going to do any others right now, but so we had 3 different ways that we could make it fair. And this, if you were the designer of this game, you could take any of these strategies. Okay? We could change all payouts. All the winnings.
So where do we got all the numbers from? Like 10, 150, 450?
This 1050, 450, 150, we changed all of the winnings up by 50 cents.
Okay, so we just shifted.
Okay. Yeah, we shifted it all up 50 cents. For this third strategy, though, we said we want to leave it at $1 and $10, but let's change the middle one so it would work. And we could have actually done that with any of the 3. We could have left the 4 and 10 alone and changed the 1. Okay. Yes?
For that last one, did you really need to do like all the steps? Or could you just say that because you were short 50 cents and there were 3, you could just multiply it by 3 and add it to 1?
Not because there were 3. You were short 50 cents, and the probability is 1/3. So you would have needed to add 50 cents twice or 3 times.
Well, you know, because like for the change all winnings, you add 50 cents
To each one.
To all 3.
Mm-hmm.
So could you just channel that 150 cents into 1? Like, does that always work, or is that just?
No, because the probabilities are different. Okay?
Okay.
Because you have a 1 in 3 chance,
That's just.
it was 53 times that you had to add. If we wanted to change the winnings for a 1, 2, or 3, we could just increase it to $2.
Okay.
To do this, we would need to increase this to $13 if we were leaving the other 2 alone in order to make it fair.
Okay.
Okay? So, yes?
What's K?
What?
What's K? Like if they said define K.
I have
Not
no
for
idea.
this problem, but like in general. What's
Let's
K?
K can just be a variable. Okay? So you have to look at the problem
It can
there.
be anything you